Hello everybody, let me bring the microphone close. Hope you all had a good weekend and are ready for the test on Thursday. So, the latest news in the exam is that virtuals may not actually be in the test. So, I'm not 100% sure on that, but let's put it this way, if they are, they're not going to be harder questions or in-depth questions, I think. Okay, so that's the latest news. Basically, the test is being made as a collaboration between all the instructors, so you'll get different flavors of questions. You will do your best at answering the questions, but ultimately, try your best. And if a question is found to be too hard, or you don't finish the test because there's too many questions and things like that, don't worry about it. There will be some sort of curve or something. So you just do your best, and I'm sure we'll be fine. So anyways, we will talk more about the exam on Wednesday. So please come prepared with questions about that. Otherwise, I'll try to do a brief review. However, that strictly depends on how I feel, because fortunately I'm going to the dentist tomorrow. So I'm going in the morning. So hopefully by Wednesday I'm okay. But if they do something big and I can't talk, then we may not have like a live video on Wednesday, and we'll just do text. I don't know, we'll figure it out. So stand by on Wednesday's class. Fingers crossed everything goes okay. So yeah. Nobody's saying anything, so I hope that we're live. Let me check. Make sure that there's a stream going. All right, yeah, we have viewers. Cool. All right. So yeah, I've seen the questions. It's not too bad, by the way, the test. I feel like most of them are nice. Some of them are multiple choice. So hello. Some of them are multiple choice. So that's pretty nice. So yeah, I've mostly been focused on making the exam for the 302 class. Thank you, appreciate it. I do hope that I am okay. So today we are going to continue talking about virtual and wrap that discussion up. I want to talk about something that I've talked about in the past, but now in a little bit slightly more virtual focused approach, I suppose. And then pretty much that the rest of this class is mostly filling stuff that I kind of wanted to mention at some point, but I didn't, such as maybe function pointers, pointer arithmetic in general, that cool thing about accessing private variables that I usually do, which I really didn't do this much this time because we don't have an assignment on that. And then if we really don't have anything else to talk about, then I'll start talking about exception handling. Otherwise, we'll leave that to the next class because that's the next topic. And it's more of I don't think we'll reach that, but if we really have nothing, if I run out of things to talk about, then we'll just go to that topic. Okay, so let me go ahead and remind you about the diamond problem. And we'll see how this goes, because it hurts when I talk. So here I have a picture that I'm just going to bring in because I like this picture. I drew it over the summer, I guess, in the summer class. And it's actually readable, so let me zoom out so I can paste it properly. Okay, so I was going to do this right before the class, but I got really stuck on doing the 302 exam and changing stuff. So yeah, okay. So basically, I want to remind you first of all about up and down casting, and up casting being when they're all with pointers, right? You got pointers pointing to objects of classes, right? Up casting is where you are basically creating a pointer of a superclass or a base class, whatever name you want to choose for that. Parent, super, or base mean the same thing. And then you're making that pointer point by assigning it, so if you're let's say P is the pointer of a class, it's parent class, like PP. And then you have a derived class that's the child class, that's C, right? And so you might have that being stored in a pointer too. Well, if you go ahead and you assign that pointer there, the child, to the parent, so now the parent is pointing to the child, That is upcasting. And it's okay to do. Like, it's safe, because if you have a class object if you have a class in general that is derived from parent class, and therefore you have an object of that class, it's going to contain all of the members from the parent class. So there should be no problem whatsoever in not having any of the variables. However, if you're not using virtual and the derived class overrid some of the functions that were in the parent class, then it's going to be calling the parent version of those classes unless you use the word virtual. So anyways, upcast, that's I suppose the only risk associated with upcasting that you can solve with virtual. The bigger risk is when you're doing downcasting, when you have a parent object and have a pointer that's pointing to the parent object, and all of a sudden now you have a pointer of a child object that's pointing to the parent. That is very risky to do, because you may fool the compiler into thinking that this is a derived class object, which may have extra functions and variables, which the object doesn't really have because it's a parent. And so if you try to call those functions, or you try to access those variables, you're going to run into big problems. Therefore, the only way that the compiler will even let you do downcasting is with the dynamic cast, I suppose, keyword. It's not a function, but it's a keyword, I suppose. And so dynamic cast is a type of casting that does some checks at runtime to make sure that it's a valid cast, and that you're not trying to actually, like, you're trying to, if you're doing downcasting, it's because the object is really a child object, and it was just being pointed because you did upcasting at some point earlier in the program. That's okay. It's not okay when like I said, you're really trying to downcast something that is not a child object. It was actually a parent. And so the dynamic cast will check that at runtime, and if you're doing something bad, then it'll return to you address 0, which you can just check with an if statement. See if it's 0, which means that the cast failed. So that's the good thing about dynamic cast. Reinterpret cast will still do the cast even if it's bad. It just because it doesn't do any checks. So that's why I discourage you from using that unless you have a legitimate reason to. It's like I call it the YOLO cast because it just goes until it crashes, and so you have to be careful about using it. It's great power comes with great responsibility kind of thing. So anyways. Now, moving into the diamond problem. So the diamond problem was a situation where we have different classes and we have multiple inheritance. If you remember what multiple inheritance is, that's good, because it's going to be asked on the test on Wednesday. And if not, then let me remind you what it is. Multiple inheritance is the concept of you have a base class, okay? And you want to expand that class or extend it. What you do is you make a child class, right? And you add some stuff. Cool. So that concept of basic inheritance is very, very useful, but there's situations where sometimes you want to make a new class, but you want to base it off of more than one parent class. And so you may have a situation, ignoring the A, just look at this part, you may have a situation where you have this class B and C that are really cool, you got lots of great features, and what you want to do is you want to make a combination of those classes into one big class called class D, which takes those classes, combines them, and even can expand upon them, right? And so that's the concept of multiple inheritance. You're inheriting the traits from multiple classes, and it doesn't have to be limited to 2. You can, I suppose, in theory, have as many as you want. This, of course, does have some risks associated with that. One of the basic ones is that if you have 2 variables with the same name that are being inherited, so like if class B and C both have a variable X in them, you run into some ambiguity problems when you're trying to access those variables. And that's what ambiguity. I gotta think how to spell ambiguity for a second there. And that is why, that's kind of what I showed you back a couple of weeks ago. And one of the solutions for that, it's kind of not the best, but it works, is you can use a scope resolution operator to clarify to the compiler which classes X are you talking about if they both have a variable X in them. Okay, so that will solve that ambiguity, but it's kind of bad because like if two classes have a variable by the same name, more than likely it's because they're the same thing and you really only want one copy. And so this can be a bit of a pain. But that is not something you can solve, by the way. Like, that's just kind of poor class design if you have a situation like that. And that's not the diamond problem yet, okay? That's just if you have two classes with the same variable. You can use this to sort of work around that, but it's not the best. Now, are there cases where legitimately you want to have two variables with the same name? Sure. Maybe it's some sort of count variable that is strictly related to objects of B class, and maybe it's a static or something. And in those scenarios, I could legitimately see how two classes could have something like a count. And it will be actually useful to make sure you clarify which count you're talking about by doing that code. So some cases it's legit, but most of the cases I would see in early, like people who are just starting the program, it's probably because they did some bad planning ahead of time if they run into that situation. Okay? So anyways, multiple inheritance is such a big issue that some languages like Java just flat out tell you like, nope, we are not allowing that because it causes more problems than it solves. That's kind of getting into like an argument I don't want to get into whether it is good or bad. I'll just tell you that in C++, you have it and you choose how to use it. So anyways, let's talk about a special scenario about multiple inheritance, and that's going to be the diamond problem. So that is where we have this structure. So we have a class A, and class A has some functions and variables. In this case, it has a foo function and an int x function, or variable, sorry. What you're doing is you have a class B and C that are deriving from A. So if I was to write the code for B, as you can see there, we have class B is being inherited from class A. Okay, now ignore the keyword virtual. That's actually going to be the solution, but for now, let's just imagine without it, and I'll code it up in a minute here. Okay, so this class B is inheriting from A. We also have class C inheriting from A. Okay, in addition to inheriting, they have their own extra set of features that they're adding. In this case, B has a variable y, and C has a variable z. Okay, so I'm adding those extra things just to kind of as a placeholder to point out that you could have billions of variables in here. Well, not billions, but hundreds. No, not even hundreds, hopefully. Dozens of variables, okay? But you could have other stuff in the classes. I'm just putting the most basic example. However, and this is again sort of poor programming design potentially, I would say, but not necessarily. There are cases where this would legitimately show up. You are inheriting, you're creating a class D that's inheriting both B and C. So the problem here arises again with the ambiguity. But the ambiguity is originating from the fact that both B and C have a copy of A in them, okay? If I was to kind of visually draw how inheritance works, you know, I would think of this square here as A, okay? And if I want to inherit A and make a class B, it's kind of, at the risk of confusing it with composition, it's kind of like saying that B is kind of part of A. Now, why I don't use this example when I'm teaching you inheritance is because it can be very easily confused with composition and aggregation. That is like if you have a class, let's say we have a class E, and class E happens to have a member variable of class B or of class A even. Okay? That is composition, right? Or aggregation, where you basically are having entire objects of other classes in there, which means you have all the variables, all the features of it, right? That's the other way of approaching this. Or approaching the idea of extending a class. Whereas if you're doing inheritance, what you're really doing is you're essentially extending the class, but everything is part of the class itself. It's not part of a member of the class, right? And so as a reminder, again, this is all good review, is that when you typically use inheritance for a sort of is A kind of relationship. So when you say class B is an A, in this case you put and because, you know, English, or if you say class C is an A as well, okay? Or D, in this case, class D is an A and is also a C, okay? Is a C or is and C, I think. I mean, it's a C. But yeah. So that is the inheritance concept when you're thinking of something based on it being something else. Whereas composition aggregation is has a relationship. So like in the case of E, we're saying class E has a B and also has an A. Okay? So that is a good way to sort of, verbally help you to think about which method you should use. Okay, it's a nice little trick, but there are, again, weird exceptions. So anyways, so when I do this picture, please don't confuse composition aggregation with inheritance. Okay, just think about it that way, as having B having an A, essentially. Okay, and so C is the same way. There's also basically an A in there. The problem arises that if I decide to make a D, what it's going to be is going to be essentially the big box that has both of these in there, along with its own things, right? The problem is we have two A's in there. What we ideally want to do is, if we're inheriting, is we really only want one copy of A. We want to get rid of one of these. Doesn't matter which one we get rid of. We can get rid of that one, or we can get rid of this one. Doesn't really matter, but we want to get rid of one of them, okay? And so virtual is going to allow us to do that, and that's going to be a solution to this, okay? So let us go ahead and just quickly code an example of that. So we're going to create a class, and I believe I have examples of this on Canvas as well. The whole parent, grandparent, whatever. So I'm just going to do the class ABC like I have here in the picture, so it matches. In fact, let's switch over to the other thing here. I think it's, which one is it now? There we go, this one. Okay, cool. And then let me make this smaller here. Have any of you seen the light boards out there? The ones that like people draw, like I'm drawing and it's like shows it. I might post a survey on Discord or on Canvas to see if you would be interested in me actually getting one for teaching, if that would help you, or if the iPad's better. Because I need some data before actually just going out and purchasing this and nobody likes it or something. Because the iPad's pretty cool too, I'm not gonna lie. It's less effort, like hand effort to move around. But anyways, we're gonna just make a function foo. There's really nothing in the function. We can add stuff later if necessary, but I think this is good. That's it. And I guess public. Okay. Now we're gonna do class B, and class B is going to inherit from A publicly. Again, just gonna have to deal with getters and setters and all that to make things fast. And we'll add a Y, and maybe we add a function called bar. I don't think we'll need this function, but I'm just throwing it just in case I want to do something with it. Class C is basically going to be the same thing as B, but in this case, it has a function called oof, and it has that Z variable in there. And finally, we really like both B and C, how they're extending A. We kind of really want to have both. So we're going to go ahead and do that. We're going to say public A, B and C. We could have A, but we don't need to. We already getting two of them, so why do we want a third one? Okay? And then don't forget these semicolons, which I always forget. I really don't like why those are required. Yeah. Okay. And then maybe this has more stuff in it. Void, boo, and maybe like another variable called, shoot, I ran out of letters, W. Okay, so just make them public again, and we should be good to go. Okay. Yeah, we haven't run out of space, so I'll still get rid of these spaces just to ensure that I have enough space for examples here. Okay, so again, the issue arises if we make an object. If we make an object of b called b, you know, no problem. We can say something like cout b plus plus. I don't know. B is gonna have some value in it. B dot x plus plus. You know, I'm assuming that it's gonna get maybe it shouldn't, like, we don't trust it as well. We initialize the variables manually. In fact, you know what? Why don't I do that myself here and just compile with 11? So let me set these all to like different stuff. Okay, so that way, if we compile with 11, then this will be okay. All right. So now I just need to put a semicolon, and I'm good to go. Okay, so in this case, you know, this should print out a 1. Or, sorry, actually 0, technically, because the pre and post increment, right? So we see the 0 right here. Right there, okay? And so there is no problem here with the ambiguity because B only has 1 copy of A. And the same thing could be done with C. You know, in fact, here, just to make things fast, I'll just change it right there, C. And if I run this again, you can see it has 0 right there, okay? So this is no problem. The problem comes in with the D, because D, if we try to make the same thing here, we just copy paste it, but this time, you know, we make that a D, and then comment this one out because of naming variables. Or here we can just change them real fast. Make this a D here, and D. This is running into the issue. And I'll get rid of this for a second so you can see it. There we go. So this is running into the ambiguity issue, okay? And it's the issue that we can solve by using the scope resolution operator. So I can say something like B. Okay, and if I do that, I solve the problem, but it's not ideal because I have 2 copies of it. And if I go ahead and cout these C scope resolution X, and then maybe this one I don't plus plus, but technically speaking, if it was accessing the same one, then this would have a 1 because of the post increment. But you'll see that it still has a 0, as seen there. Okay, so and I suppose similarly, let's try calling foo, because there's 2 copies of foo, right? So like, who's getting called with that? Like, what is that? You know, and again, it's ambiguous, right? There's 2 copies of foo technically, and this one's even kind of more abstract to think about because, like, check it out. It says that foo's ambiguous because there's 2 foos that are coming from like the foo in B and the foo in C. But like in this specific scenario here, they're identical because neither V or C are overloading or overriding, in this case, yeah, overriding, are not overriding the foo from A, right? Just to make sure you guys remember override versus overload. Overloading means you have a function that takes different parameters, right? So like if you have the function foo, and then I go ahead and make another function foo that takes an int x, and then maybe one that takes an int x and also an int y, that's overloading. Overriding is when you flat out are replacing the function, such as when you typically do with virtual, right? And so in this case, we're not doing that, but it's still ambiguous. Like, so here is a case where the compiler is being so strict about this, is not letting us do something that should really work. But then again, it has a valid reason to do that. So anyways, I can technically do the same thing. Oh, wait, not A, again, B or C. I can put in B or C in here and be okay, I suppose. But like, that's horrible, you know. Like, ooh, scope resolution operator for a function. So how do we solve, for example, the foo? Well, the foo we could solve by making it virtual. Actually, will doing that just fix it completely for the foo? I'm not 100% sure actually on that. It's still ambiguous, yeah, because even though it's virtual, there's still 2 of them. So that's interesting that it does it like that. So yeah, so that won't fix it either. And even if somehow that fixed that, we still have the problem with the variables. You can't make variables virtual. That is a no-go. So even if we could fix foo by actually writing different foos for each function and solving that issue, then we would still run into the same problem with the variables. And so the solution is to make the entire class virtual with what is known as virtual inheritance. Okay? And what virtual inheritance is kind of like, again, taking the concept of a virtual function and applying it to an entire class. So what it's going to do is, with the virtual functions, what it does is it doesn't link the function until runtime, right? Compile time binding versus runtime binding. With virtuals, with classes, what it's going to do is, if two classes have each a copy of a superclass, in this case A, and then we're doing the multiple inheritance, what ends up happening is you have only one instance of the class being copied. So like when you're making D, the recipe is like run B and C, right? The constructors for that. And so it looks at B or C, I'm not sure which one first, probably B because the other wrote it. And it's like, okay, yeah, we're getting all the stuff from B. And what does B require? All the stuff from A. So it also gets the stuff from A. Then the constructor for C is going to run, and then that's going to say we need all the stuff from C, which requires all the stuff from A. But instead of getting the stuff from A, it's like, hey, we already have A from B, so don't kind of import that in here. So then it doesn't run that. And then it just gets the stuff from C. And so what you end up with is only one copy of A, which is what we're looking for. And so how do you achieve this dark magic? Well, as you actually saw earlier, all we got to put in is the keyword virtual in both V and C. You don't put it necessarily, I believe it doesn't really work if you put it on the superclass. You have to put it on the derived classes, because what is happening is you're telling it at this point to make the inheritance here virtual. So only, you know, like when it comes to time to actually use this class, and do you check whether you need to import or inherit it, in which case you do one time, but by the second time it runs, it's like, oh, no, we already have this in here. So that's why I believe you put it at this layer here. If you were to put it at D, then I believe it would be already too late. So now it compiles and it runs, and we can see that the output changed from 0, 0 to 0, 1. Why is that the case? Because now we no longer have two copies of X. And so when you see line 25 here having the B X++ and then the CX here, they're actually now, even though you can still access them with the scope res operator, they're now referring to the same variable, which is why the second time you run it, the increment takes place. Because post increment, remember, it pulls the old value for the C out, but then increments it internally. So the next time you print it, it's the incremented value, right? So that's we're getting 0, 1. But furthermore, you know, we no longer need the scope resolution operator for any of these things, or like, for example, for any of these really. But I'm gonna actually leave it back so that I can give you that code so you can play around with it. But as you can see, we don't need it for any of them. But I'm gonna go ahead and throw it back. Just leave it there in case that you want to experiment when I post this code online. And yeah, does it make the members like static? Not quite, because with static, well, I guess if you think about the mentality that there's only one instance of something with static, I suppose yes, but that might be misleading to think about it that way. Because the idea with statics is that all classes share an like a member variable, in like an int x or something that was shared amongst all of them. There's only one of them, right? However, with statics, no matter how many objects you have, there's only one copy. With this, with virtual, yes, A only has one copy, no matter how many copies there are. However, if I go ahead and make another object of D, so like I'll call it D2. That has its own copy of A in it, right? So like it has its own X. That one is not shared with this guy, which static would mean that it is. So I just want to make sure that you don't confuse that. And you, by the way, you can also put a static variable in here. Oh, well, now I got to remember how to initialize a static. So that would be int A : S equals 0. I believe that's how you initialize a static. It's been what, like 2 weeks? S does not name a type. Oh, well, I forgot the word int in here. There we go. So now with that static in there, if I was to, you know, and then maybe like, here, let's create a constructor for A. Every time that an object gets made, S gets increased. And so now, let's go ahead and see out D2's S. And let's see how much that is. So let's think about that actually, because I gotta think about that for a second, right? Because there's only one instance that is supposed to be made for the D class. We should see S to contain the value of 2 in it, which is just this one and then this one, right? Whereas in the other system, it would have a value of 3. But I'm actually curious how the constructor will handle this. So this is actually like cool. So let's see. So we see a 2. Okay, that's good. That is what I expected to see. But if we take the word virtual out, let's see if we get a 3. I think we would get a 3. Because now we have 2 copies of A, right? So I think we should get a 3, but we'll see. Oh, we got a 4. Oh, I see, yes, yeah. because of this. So we have 2 copies in the first D and then 2 copies in the second D. So yes, that makes sense. I was like, whoa. But yeah. But if we add the virtual back in there, now each of them only has 1 copy, so we get 2. So yeah, makes sense. Okay, so no panic there. For a second, I was like, whoa. But yeah, that's actually cool. I have to add that to my repertoire when explaining the diamond problem. That static is useful because it's a way for A, it's a good review for statics for the test, but 2, it's a nice way to see how many objects of A really exist. Because now you can see that it was 4 instead of 2, or just 2 instead of 1 technically. All right. So anything else, or do you guys feel comfortable with this? So this is known, by the way, this concept that we just did is known as virtual inheritance. Okay. So that is the first thing I have up here. Virtual inheritance. And yes, it's very useful whenever you are trying to solve things like the diamond problem. The diamond problem, by the way, like I said, it doesn't have to be just 1 layer or 2 layer. Like, this is kind of nice and easy to see that this is the diamond problem. But like, you know, you could have a structure like this. Like that inherits to this inherits to that, inherits that way, and maybe this inherits here, maybe here, and then like that. Okay, that is a lot trickier to see the problem, because like you might not see all the way up here that this is shared, right? So therein lies an issue that you'd have to think about. So like you'd have to put the virtuals on both of these, right? But it might be harder to keep track of that. And you could see something like this layered, you know. I've seen it in like game code and stuff like that. Like you have different layers, like start with an entity, you go like a delete like a active entity, then you get like a player, certain class of a player, and so on. So like you can see different layers like that. So yeah, okay. So moving on, the next thing that I wanted to talk about is pointer arithmetic. Okay, cool. So I've mentioned pointer arithmetic throughout, but I haven't like formally messed around with it. So that's what I kind of want to dedicate the folks to, you know. And like I said, we can spend the rest of the class on this. In fact, you could spend the full semester just playing with pointers and still run out of time. So first of all, let's refresh our minds about memory. Okay, so first of all, remember what you see when you print out items is hexadecimal, right? And hex goes from 0 all the way into, it goes to 9, and then from there it goes to A, B, C, D, E, and F, which is basically 10, 11, 12, 13, 14, 15. So there's 16 different digits or symbols, 16 different symbols that represent this base 16 numbering system. And again, we use letters because everybody knows how to, well, not everybody, but everybody in the Western society who uses this kind of alphabet knows how to draw these symbols. So, I mean, they could have just as easily invented new symbols, which frankly I think would have been cooler. They would have, I don't know, there's 9, and then we get like 10, and then that, and man, I don't know. At this point I'm drawing like random stuff. I don't know. Hopefully none of these mean like weird things. But yeah, so you could have like, we could have just invented random symbols, you know. But no, they were like, whatever, we'll just use existing characters. So anyway, that's hexadecimal. And so our memory system in the computer, and again, in 219 they'll really talk about this, is kind of shown like that because at the end of the day, you know, it really is more of like sort of like in like one. At the most basic level, there's like little ending and big ending, which we'll talk about, so I don't want to get into that. But it's just a bunch of zeros and ones, okay? And so what it does to make it simpler for you as a programmer to deal with is instead of just giving you all the zeros and ones and saying like the first 01 is at like address 1 and the second 01 is at address 2, like that would be horrifying because a single integer typically takes 4 bytes. And 1 byte is 8 bits. The bits are going to be the zeros and ones, okay? So that means that, you know, if I write here 8 of these, so like just a mixture of zeros and ones, so we have 1, 2, 3, 4, 5, 6, 7, 8. This is how much data is required for 1 byte. For 1 byte. An integer is 4 of these. So I gotta like basically have 4 of these. I've already run out of space. Shrink them. Okay? So that is what an integer would look like if you want to see the actual bit representation of it. Okay? Imagine if our addressing system was like that. Like you would have to shift by 32 every time that you wanted to go to the next integer. And so to make our lives easier, instead of putting the addressing by bit, they do it by not just bytes, but actually multiple byte increments. Typically, you will see in 4 byte increments. But at least when you're seeing hexadecimal, the hexadecimal represents each byte, okay? So if you're seeing an address like this, you can think of that as like the, well, not 100, but 101st byte in the system, assuming that, you know, the addressing starts at 0, okay? And so the next byte is going to be at address 101. And then from there, it'll keep going until it gets to 109. And then from there, it's going to go 10A. And then it'll keep going until it gets to 10F. And finally, from there, it's going to go to 110. Okay? And so on. It's going to keep going until it gets to 190. The last thing will be actually 19F. And then from there, it would get to 1A0. Okay, which looks a little bit weird. You gotta get used to that base 16. All right. So, anyways, we do the thing in byte increments because we don't really deal with individual bits because that would be a pain. And so, there's no easy way actually to try to access like within a byte, which is made up of 8 bits. There's no easy way to access those individual bits. There are, however, bit shifting techniques and other things you can do to access the data of those bits if you want to individually transfer stuff. I made him do a 219 project that's actually related to that. So you'll learn about this, okay? Right here, we're kind of going very briefly about this stuff. Because, you know, first you learn programming and then you learn how it actually works in the computer. So, now that we understand that, you know, when you see something at an address like address 200, and then you see that the next address in the system, like if you're printing out an array. So let's say we're storing an array called A that is of size 5, okay? So that means that there's 5 indices in here, 0, 1, 2, 3, and 4, okay? And so when you do that, the system is going to give you how many bytes? Well, if each one, well, I suppose I should say, normally an integer takes 4 bytes, but it depends on the hardware. Some hardware, older hardware, I believe it took 2 bytes. And some hardware, like modern hardware, might give you 8 bytes. Like there's no written rule per se. It's up to the people that are making that system and the architecture and organization to figure these things out. But as a common norm, I see nowadays 4 bytes. I think that's pretty much standard, okay? And so, if we assume that to be the standard, then in this case, how many bytes would it take to store this array? Well, you would multiply 4 times the size, which is 5, which is 20, which is why when you're doing the malloc allocation, you know, if you remember, that was like malloc, and then you would do basically size of int times 5 in this case. Size of function is basically getting the size that the type that you're trying to create an array of is in that specific system. So in that specific system, when you're running the program and the integer is 4 bytes, then this should return to you 4, which you then multiply times 5, which you get 20. Now, why don't you just write 4 in there instead of int? Again, you want to make your code portable in the rare situation that an integer was a different size in that system. And so the 5, of course, you know, you would put a variable there, not unless you really want to hard code it, in which case, while you're doing malloc, you could just do the above right here. But, you know, that's kind of the idea. So anyways, that would actually get stored into these 5 addresses. We have address 0, 1, 2, 3, and 4. And while, again, in 219, how it gets stored and how everything is put in memory is totally different. What you're looking at it, and you know, when you're looking at addresses, are virtual addresses. They're like the nice and happy rainbows, everything is great version of how addressing is actually stored. You see everything as just a contiguous block of memory. Internally, the inner workings are dark and evil and all messed up and confusing to keep track of and a headache. Meant not because, you know, they don't too much effort kind of thing, but because like there's a lot of stuff going behind the scenes to speed up your computer the most possible. There's things such as cache, and because of caching and paging systems and things like that, essentially there's a lot in background of what is coming in and out of memory to be able to maximize the fastest type of memory in your system versus the slowest type, right? I mean, think about it this way. You got a program like Warzone. Call of Duty Warzone takes like 250 gigabytes of memory. You can't store that all in RAM to make it super fast. It has to pick what to store and what to keep in the hard drive, right? And so, furthermore, the RAM is slow too. There's something known as cache, which is memory that's really close to the processor, and that's actually different layers. Cache 1, 2, and 3. I believe some computers might have 4, but like the standard is 1, 2, and 3. And so, the one cache, L1 cache is called, which is really close, it's really tiny. We're talking on the megabyte size. You want to put in there the stuff that's most frequently used. And then the L2 and L3 is less frequently used stuff, and then you get the RAM and finally get the hard drive. Being able to coordinate and move things back and forth as needed is a very complicated process, which you learn in 219. And so I have videos on that on YouTube if you're curious. You can go start watching those now before you take 219. You know, whatever. That's good. More knowledge is better. But essentially, for now, we as developers do not have to see any of that in it working, which is frankly a blessing. We don't need to deal with that when we're trying to code like hello world. So what we see is everything is nice and contiguous and yay, okay? So that's where we're kind of going on that assumption. But the reason I wanted to point that out is A, we had the time to do it, and B, I don't want you to go and argue with somebody that has taken these classes who they're like, no. Stuff is not stored in like a nice order. And you're like, yes, that's what he told me. Why? He lied to me. So no, I'm not lying to you, but I am oversimplifying it because you don't need to know yet. You don't need to know the truth yet. The hard, dark truth. Okay? So, yeah. Okay. So this would be an example of how this array is being stored. We have address 200, not 200 because it's hex. Hex 200 is not the same thing as decimal 200. And then we got the next address, because it's going in increments of 4, is 204, 208. Then you get 20Z. If we look here at the list of numbers, if we go from 8, so like 8 would be here, you go 1 byte there, 2 bytes there, 3 bytes there, 4 bytes there, which means the next set starts at C. From there you get 1, 2, 3, 4. The next one starts when this goes back to 0. Okay? And so that is why this goes from 8 to C to 0 again. Okay? So when you create an array, whether it's dynamic or static, malloc or new, doesn't matter, what you get back, if you were to look at what's in A, so doesn't matter if I'm making it like this dynamically, like int A. I mean, yeah, you gotta cast it or whatever in C, or if I'm using new. Doesn't matter which method I'm doing. What A contains is the location, and by location I mean the address of the first element or the first index of the array. Okay? So that means that the pink/purple address is what you would get back if, in the case of dynamic, if you did cout A, which is the pointer, or in the case of static, as long as it doesn't give you any errors, I suppose, if you did %A. Okay? Assuming this code up here. Obviously, don't do them in the same code because naming conventions, but whatever. That is what it contains. Furthermore, let's switch over to dynamic for now. If this is the address of the first element, you can use what is known as pointer arithmetics to identify the other locations in the array. So pointer arithmetics is the idea of adding and subtracting numbers from an address. Okay? And it works a little bit differently than normal arithmetic does. Normal arithmetic, you have 8 plus 2 is equal to 10, right? Okay. 8 plus 2 in pointer arithmetic is going to actually be equal to, let's see, 8 and 8. So that would be 16. So it would be plus 16 of 8, which would be, 24. Okay? So that would actually be the equivalent of pointer arithmetics. But however, it wouldn't be spelled out as 24. It would be spelled out in the hex equivalent of 24, which was what I was trying to think, but I could not, so I gave up. But it would be 1, which would get us to 16. So 1, 8. Yeah. Oh, well, that's easy. I didn't think about that. Yeah. Yeah, you just have to, because it's of increments of 8, this basically just shifts this one full circle around. So like if you did plus 2 again, this would just become 28 like that. Well, not 28, but 2/8, because this is hex, right? So the way pointer arithmetic works with addition and subtraction is when you have an address. So let's say let me write a concrete example here with pointers. So int A gets new int 5, right? So we just allocated this array that I was showing you above. Okay? So forget memory leaks for a second and whatnot. In fact, actually, don't worry about them. Yeah. If we go ahead and say cout the reference A, what would this print? Well, A is the address up here. So let me copy this down as well. Let me shrink it as well. Let's just say that there's random garbage in here. Let's just put in some numbers. So like 10, 5, 3, 42, 9. Okay? So let's just say that's what's contained. Well, how is that contained, by the way? Binary representation of that. So, for example, 3 in binary is 1, 1. So what you would find, it's actually 2's complement. What you would find in that location, in address 208, would essentially be a bunch of zeros, 30 zeros to be exact, and a 1, 1 at the end of that. Okay? That's actually how you would store the number 3 in memory. But anyways, A itself contains, because A is a pointer, and A is stored somewhere in memory too, right? Now that doesn't have to be contiguous even in our nice and happy world of memory. So like somewhere here at address 9AB, for example, could be our A pointer. Okay, our A pointer is always static. Even if it's dynamic allocated memory or static array, whatever it is, the pointer itself, in the way that we declared it here by putting it into A, means that it is static as well. Okay, no matter how dynamic you want to make a program, you will at least need to have one static variable, which is going to be a pointer, which can then point to everything else dynamically. But you need somewhere to start off with. That's just kind of, you know, the challenge. If you try to come up with something that doesn't use anything that's not dynamic, it's impossible. So, yeah, anyways. So what is contained right now here is address 0x200. That's stored in binary too, but it will be the binary equivalent of that number, which in decimal is going to be a big number too. But I don't feel like converting it. Probably like, let's see, hex to des. Oh, well, that makes sense. 512. So if 200 in hex is 512 in decimal, which in binary is going to be 1 followed by a bunch of zeros. How many zeros? Probably like 8. 2, 4, 6. 2, 4, 6, 9. Not 8. I think we got 9 zeros there, right? Yeah, we do. Okay. So that's in hex, that's in decimal, and that's in binary. So if you were to look what is contained here, it would actually be this right here. Okay? And if you were to look what is contained here, you would see, like I said, in binary, 30 zeros followed by 2 ones. Okay? So, when I say cout asterisk A, all I'm doing is I'm dereferencing this address, which is address 200. So this would actually print out 10, which is also the first index of my array. If I also did cout A0, that would also print out 10. Okay? Now here's the interesting thing. With pointer arithmetics, what I can do is, if I do cout A like that, I know that this is going to give me address 200, which is the location, you know, what's stored in A. If I do this, A plus 1, I'm not going to get 02001. What I'm going to get is the equivalent of the pointer arithmetics answer, which is, when you see a plus 1 to a pointer arithmetic, what it's going to do is going to increment the value of A by the size of what A is pointing to. So A is an integer pointer, and this is why it matters what type of pointer you're dealing with. A is a pointer. What kind of pointer? It's an integer pointer. Integer pointers in the system here are size 4. You can confirm that by doing size of or whatever. You can think of that internally. It's doing a size of function call to figure out that it's 4. And when it figures out it's 4, what it's going to do is it's going to increment the address of, you know, whatever A contains by 4. Now in this case, it's not modifying A itself, because it's just like if I said, you know, if A was a regular variable, not a pointer variable, and I said A plus 1, and the A contained like 8, then this is the answer is 9, but I'm not saving that back in A, right? So it's just kind of blurring it out. If I want to save back in A, I would have to use the assignment operator. So I could do something like A equals A plus 1. Now that would actually permanently modify A, but I'm not doing that. Okay? I could, but I'm just not doing it in this example. So what will be contained after this line of code would actually be, or what will be cout, sorry, would be 204. Which means that if I try to dereference that, this would print out the number 5, which is the contents of essentially the same thing as saying A sub 1. I'm going to start writing cout now because it takes too much time. Okay? However, you probably want to put those because I believe that the asterisk has higher precedence than the addition sign. Okay? So you want to make sure that the addition happens before the dereferencing. So you want to make sure, you know, you get 200 plus 4 before going to address 204. Okay? Similarly, if I went ahead and said a plus 3, what is that going to do? Well, that's going to add 200 plus 3 increments of 8. Oh, sorry, 4, because that's the size of the integer. So it's ask us what's really happening is 200 plus 12, which of course would be C, right? Because the 12 is a C in hex. Yeah, because A is 10, B is 11, 12 is C. So this is the basic of pointer arithmetics. Let's go ahead and try something else. Suppose I did a minus 1. What would this print out? Well, actually, it would print out some garbage, or maybe it's sec fault, but it's actually printing out what is an address 1FC. That would be 200 minus 4, essentially. Whatever is in this address is just going to get printed out here, assuming you don't sec fault because you're going out of bounds. Going out of bounds is an undefined behavior in C++. Undefined behavior means that it is not something that the people that created C++ decided like this should happen to it. It's kind of like they left it blank. Like the people that created C++ did not mention it, and because of that, it's undefined, which means it's up to the compilers or up to the runtime systems to interpret that and do what they choose. So that is why in some computers this may crash. In other computers they might access the array and be okay. It's unknown. It's not something that is consistent across the board, which is why we make use Sally for this kind of stuff, to avoid undefined behavior like, you know, my program works okay in my computer, but it doesn't work in the TS computer, so like that kind of thing. So anyways, the address here again would be 1FC, which is, again, if you think about how hexadecimal works, this is correct. Otherwise, just go home and practice on your own, or you're already home, but wait until the class ends. So, you know, if I went ahead and did a minus 2, or here in this case, let's just, without dereferencing it, this should print out address 1F8. Yeah. And a minus 4 would have been 1F0. Okay? So that's the basics of pointer arithmetics and how they work. You can also use pre and post increment. So if I went ahead and said cout I don't remember which has higher precedence. I'm going to assume that the pre and post increment has higher precedence, but because I'm not sure, I'll just put it in parentheses, and you know, you can test it on your own to see what has higher precedence. But yeah, if I do that, but if I do that, is it going to take the old value of A or the new value of A with the parentheses? I think it'll still take the old value of A, but I'm not sure. You know, we should test that actually if we have time. I'm curious. Let's see. So we don't live with the question. So let's go ahead and say cout, or sorry, int A gets new int 5. And then let's go ahead and say cout. Or here, let's go ahead and initialize that. So for int I is equal to 0, I is less than 5, I plus plus. Let's just go ahead and say a sub I. Actually, instead of doing the a sub I, let's use pointer, because I was gonna say we're just gonna initialize it with the value of I, right? So like if this runs, you know, which it should, I hope, g++ mid1 that's p, and then do another for loop for printing it out. So this should print out basically 0, 1, 2, 3, 4, 5, right? Or 4, okay? So here, check it out. Instead of using this system here, let's use pointer arithmetics to initialize our array. So how can we do that? Well, we can use the plus sign, and then we can use our parentheses. And the reference that location, and as you can see, that works the same way. Now you might be thinking like, oh my gosh, why would I want to use this syntax when I have these nice square brackets? There are some scenarios where it's useful, but I do agree with you in general that you don't want to use it unless you're trying to confuse somebody. However, that doesn't mean that somebody else is not going to use it to try to freak you out, or just because they don't know any better, or they're just trying to be fancy. And so, you know, it's good for you to know how it works so that you don't get that, you know, confusion if you see something like that. So, and the same could be, you know, I could replace this exact line of code with this right here, and that would also work the same. But I'll leave the other one as is, so you can see that they're both equivalent. So, let's go ahead and actually try out the, oh here, let me print you some addresses so you can see it. So maybe in addition to printing out the, or not in addition, this is another for loop actually. Let's print out the addresses so you can see how this is actually being stored in main memory. So here, instead of couting, so I guess in this case, we could do it two ways. Yeah, why not? Let's do it this way. That should get us the address as well. And then let's do another loop, but that time let's do it using pointer arithmetics. In which case I think pointer arithmetics looks a little bit nicer. In this scenario here, we can just say a+i without the reference operator. So I suppose because this is less writing than this, I actually would say that this is nicer. But to someone who doesn't know what's happening with pointer arithmetics, that might be totally confusing. But not to you, because now you know. Let me add some end lines here so that you can see all of this. So add an end line there, add an end line here, and then we already have one for that one. So let's try that again. So as you can see, the addresses are identical whether I do it in this system or this system. But there is a good example of how pointer arithmetics makes your coding a little bit simpler. However, an argument can be said that even though this is less coding, this one is a little bit more readable. And there's a big thing they'll talk about in 226 about readability, writability, and reliability when it comes to writing, when it comes to programming languages. Because sometimes the most readable code is not the shortest code. And it is preferred to have readable code than less code. Because at the end of the day, code is a collaboration in the real world. And it's useless for you to say, oh, I wrote this amazing program in like 10 lines of code if nobody else understands them and nobody else can fix them if there's a bug. Whereas if you write 50 lines of code, but it is super clear and a lot easier to maintain, it's frankly better code. So yes, now there are extremes, of course, you know, on both sides. So yeah, I'll say that much. So anyways, as you can see here, the addresses are indeed incrementing by increments of 4. So they go from 0 to 4 to 8 to C, and then back to 0 with the 3 here, okay? So if I run it again though, I get totally different addresses because I'm getting the operating system is giving me different memory addresses to work with, but they are still incrementing in size of 4. Run it again, and as you can see, those addresses are all looking like they're from the heap. See that? So, yep, that's pretty much it. Now, let's go to the question at hand that we had, which was, what happens if I do cout asterisk a++ without anything associated to it? And then after that, let's go ahead and cout just a and see what a contains. And let's see what this prints out. So I'm curious. All right, so this prints out a 0. So that means that it is taking the old value of a and then doing the increment. And as you can see, the increment was done because it is now a is now containing the second index, which is, well, index 1, but the second number. So cool. Now, if I wrap it around in parentheses, will it be the same result? And the answer is yes. Okay, cool. So that's a good review of pre and post increment. Now, there was a question. Would delete square work on any of the A memory locations like A+1, or does it have to delete from the first memory location? See, that's a good question, because let's try to run delete now, because we've incremented a by 1. So now the only pointer that we have to this array is no longer pointing to the beginning of the array. It's now pointing to the, if I try to, assuming it doesn't segfault, which it might, if I try to run my for loop again, it's going to print out everything plus whatever's outside of the array. So in this case, this one, okay, this doesn't segfault because I'm not dereferencing. So it prints out the second, the third, the fourth, the fifth address, and then the sixth address, even though there's no sixth address, right? But if I try to dereference that, it might segfault. It really depends on my system. It will segfault or it'll give me some garbage. In this case, it did not segfault. Yay. And it gave me a 0. Now, it didn't just like flip it around. It just happened to give me a 0. But like, you run this in your system, it might segfault, or it might just give you like a really weird and big number here, okay? So now the question was, what happens in this system now that is no longer pointing to the, I guess I'll leave that, I'll comment that out, that is no longer pointing to the beginning of the array if I try to call delete? Like, will it over delete? Will it under delete? What's gonna happen? Will it segfault? Oh, sorry, wrote them in the backwards order. And so, it turns out that it will run and it will delete the rest of the array, but it's not going to delete that first element. And I guess in my situation here, it just core dumped. Okay? So if I was to run valgrind, you would see that there's a memory leak before, assuming it doesn't, that it finishes running the delete before it segfaults. So you can see here that, I guess when I'm running valgrind, it doesn't segfault. But you can see, which is kind of nice because you can see that, oh, in this case, it just gave up. It did not even run the free at all. It has 20 bytes. That's interesting. But yeah, you saw that if I run it normally, it does segfault. So here's what happens. Internally, if I understand C++ correctly, it knows the size of the array internally. So you're calling delete, it knows that it has to delete 5 elements. And so it's deleting outside of the boundaries, which is why it's crashing. Okay? I believe, but I'm not 100% sure. How do we fix that? I think if we do a-1, that might work. Compile. Void an integer. Invalid operands void an integer? Why is the thing is a void pointer? Okay, let's try putting it in parentheses. Okay, that was weird. So there we go. No memory leaks, and it deleted correctly. So I don't know why. I guess order of precedence. Something was happening with the without the parentheses there. But yeah. So as you can see, as long as you feed it that first spot, then it works fine. So yeah, it's definitely finicky when you do that. So you got to be very careful about pointer arithmetics modifying the original pointer that you have. Okay? So that's kind of the basics of pointer arithmetics. You can traverse any array using strictly pointer arithmetics. They get a lot more complicated though if you're dealing with like a 2D array. Like a lot more complicated. Because here, in fact, at the risk of making a fool of myself, I'll try. So let's just make a 2D array, not even dynamic, let's just make it something like that. And then let's write a for loop that would print out this array. Alright, so I'm going to copy this twice. One of them is going to be to initialize the array, and the other one's going to be to print it out. So I'll just do I plus j as the number to initialize it with. Doesn't really matter much. And then for this one, I'm going to put an end line here, and then I'm going to see out that and that. No, just a space here. Okay. So if I run this now, and can you see that still? Yes. Ooh, I'm glad that I've run out of space there. If we run this, compile, run, we got our 2D array right there. Maybe we make it well, whatever, we'll keep it that size. We want to switch this line of code to point to arithmetic. It's gonna be, so first let's do the bi part. So that is just becoming b plus I, and then we dereference that. And then I think, because it's static, this could actually work, but I don't think it would work for dynamic. Let's try that. Okay, that's giving me addresses, so because I need to put this in parentheses. That is still giving me addresses. And what kind of addresses am I getting? Okay, let's try something here. Let's try doing it like this. And then putting asterisks there. And there we go. Okay, that worked. So I did it how I thought I would have to do it for dynamic, but I guess it also worked for static too. So as you can see, that is very, very complicated compared to like doing this. So you have to kind of think about it how like the arrow operator works versus like not using the arrow operator, right? So first I am going to dereference the, here, let me highlight it properly. I'm dereferencing to get to the first dimension, which is the same thing as I did before. So if you look up here, right here, line 7, I got the a plus I to the asterisk, which in this case is basically the address of b, which is my array, which could be a in the other case, plus I, and then dereferences. So it's like I copied and pasted that. And then I wrap that whole thing, and I think of that as an imaginary new b, which I just do the same thing. B plus the next number, which is j, and then dereference it again. So it's literally like, if I pop this open here, the way I'm thinking mentally about doing this is, I know for one dimension, it's a plus I, dereference, right? So what I'm doing is, well, I'm gonna consider this like mathematically to be like a variable w. And so once I get that dimension, to get the next dimension is w plus I, dereference, right? And if I consider this to be again w2, then it would be w2 plus I for like a third dimension, right? So all I gotta do now is to plug this in. So if I want to plug it in for the second one there, all I gotta do is basically take this, oops, leave it there. I'm come on. I'm gonna plug it into the top here actually. So I'm gonna put this here, and now make some space, and instead of w, I'm literally gonna replace it by this thing here, because this is what w is, like that. And so that is basically, and I'll put it down here so you can see it better. Then you squish it back in a little bit so you can see it all. That is how I came up with the second one. Except now, the I is no longer I, it's the second dimension, which is j. And this array is not called A, it happened to be called B, which is how I came up exactly with this line of code right here, okay? So, as you can see, it does get a little bit messy when it comes to multi-dimensional array. So in theory, if we had a third dimension in this array, let's say the array was called like x, then it would look like this, asterisk here, a plus here, and a k here, followed by that. I believe that would be correct, okay? But I'm just using the same systems here, okay? So if we had 3D array, what do you prefer? This or something like this? So pointer arithmetics are cool, they have their place, but they do kind of get a little bit weird and confusing once you start going to higher dimensions, at least with arrays. So the moral of the story is, don't use this syntax unless there's a legitimate reason to use it, but still understand that syntax. So if others use it, you can understand what the code is, right? Because you need to be able to read not just your own code and write your own code, but also read other people's code, be able to work with their code, potentially debug their code if that's your job. So it's important to know these. It's like, you know, you have to learn bad coding and good coding if you want to be a good coder so that you can understand other people's code. So yeah. Anyways, that is the end of the class. I actually feel much better now. So again, on Thursday you have your exam. So Wednesday will be an optional class that you guys are welcome to come to if you want. If not, then you can just take the day off. But if the class happens, which I hope it does, but depends on how tomorrow goes, we will do like a review. And if the class doesn't happen, I'll still be available on Discord or something. But it only if like my math is like in pain or something, which I hope it's nothing serious. So yeah, I mean, I'm doing it at 7 a.m. tomorrow, so that gives me like a good 30 hours to basically before the class time. So that's it. If you have any other things that you want to point out, just send me a message and I'll get back to you. But be ready for your test. Start practicing and whatnot. This stuff, this pointer arithmetic stuff, in theory, could be in the test. I don't have any questions that I added myself related to this stuff, but other instructors might have. So yes, this could be fair game potentially. Hopefully they don't put like this one in there. But even if they did, you learned it, so you should be able to do it. In fact, I kind of want to put one in there because then we'll know how to do it, but their sections won't, maybe, and then we'll look better, right? Nah, I am kidding. It's all fun and games. So, all right then. Thanks for watching, guys. I'll see you all on Wednesday.